Okay, so this is the last section before the end of this unit. We have a homework, we have another quiz, we have a review for a test, but just know we're getting really close to our first test. So the last thing is, we've talked about this already, but we want to just kind of make this idea with limits and limits at infinity a little bit clearer. And so it says, we've already seen both an infinite limit and a limit at infinity, but let's kind of get a better idea here. So here of these. So like looking at this graph, we want to think about this. So infinite limits, right? So infinite limits versus limits at infinity, two separate ideas. So infinite limits is, this is never going to fit in this box, a limit as x approaches a, where a is a real number. So you always get either like negative infinity or infinity. And this means that there is a vertical asymptote. So when your limit is x approaches a real number a, when your answer is infinity or negative infinity. Okay? So maybe I can write that over here better. If you have the limit as x approaches a of a function, and you get positive or negative infinity, that's telling you that there's a vertical asymptote. So kind of looking at these, if it says the limit as x approaches 2 from the left of f of x, so 2 from the left would be coming in this way, so that would be negative infinity. And 2 coming in from the right is going up, so that would be positive infinity. And the same thing looking at this graph, we can see approaching negative 1 of g of x, that's this other one over here, right? G of x coming from the left on g of x is going down to negative infinity, and g of x approaching negative 1 coming from the right is going up to positive infinity. So when your answer is infinity and your number is approaching, your limit is approaching a number, that's how we know there's a vertical asymptote. Where else does infinity appear on our graph? When we take the limit going to infinity. So limits at infinity is like a limit as x is approaching positive or negative infinity. When you take a limit, you could get, your answer could be positive or negative infinity or a real number. Here's kind of the big idea. It indicates the in behavior, aka the horizontal asymptote. So again, out to the side here, I'm going to kind of write this out how I like to do it. If I take the limit as x approaches positive or negative infinity of a function, and I get a number, that number is a horizontal asymptote. What if I get plus or minus infinity? Well, that means that there's not a horizontal asymptote, that the graph is just going to infinity or negative infinity, okay? So when I see a limit as x approaches infinity, I know I'm kind of thinking about an asymptote. So looking on this one, the in behavior of the graph, if I look as x goes to infinity, what's happening to my graph? Well, it's getting closer and closer to 2. And if I look at the limit as x goes to negative infinity, again, that's as x is getting smaller and smaller, it's getting closer and closer also to 2, aka the horizontal asymptote. But look at g of x. G of x, as x goes to infinity, this graph, yes, there's a slant asymptote there, but that graph is just going up, right? So that's an example of where it wouldn't have a horizontal asymptote. The in behavior, it's just getting bigger. And then what happens on the other side here, as I go to negative infinity on x, again, this graph has a slant asymptote, but it is getting smaller and smaller. So I would say negative infinity. So asymptotes and limits, very, very connected, both vertical and horizontal, and just kind of trying to keep that straight. Very easy when they have a graph, harder when you don't have a graph. So it says, now we must develop an analytical procedure by which we can find limits at infinity. Basically, a limit at infinity describes the in behavior of a function. Find each of the following limits at infinity and give an explanation for your reasoning. So some of these we should just know, right? Like you should know what this graph looks like, at least sort of. Thinking about in behavior, the way the arrows point, right? Remember my dance moves? So the fact that this is an odd function with a negative leading coefficient, I know the arrows in an odd function go in opposite directions. Yes? But do you remember which way they go? Again, all the math you've ever learned, right? You need to know it all. So an odd function, think about x cubed. The left side goes down, the right side goes up. This tells me, since it's negative, that the left side of my graph is going to go up and the right side of my graph is going to go down. So what's happening as x goes to infinity? Well, the limit here is going to be negative infinity based on the leading coefficient, based on the in behavior of that graph. I could do the same thing on the second one here. Even though this is three separate things, think about the degree and the leading coefficient, right? Stuff we've been talking about since Algebra 1. If I worked this out, I would have a negative x squared. And this one times x, which means this would be negative x to the fourth would be my leading degree, leading term on that problem. That's an even function. We know even functions, the arrows go in the same direction. Well, this one is negative, so we know both arrows are pointing down. So the limit value on this one, that's a terrible infinity sign, is also going to be, oh my gosh, I did my math wrong, didn't I? I hope you caught this. Look, I didn't multiply right. Negative x times negative x is positive x. So shouldn't that be positive x to the fourth? Which means I was right, except for I multiplied wrong. And I should get positive infinity. Doesn't help when I can't multiply. What about this one? This is where we talk about the degree of the numerator versus the degree of the denominator. Yes? So if you remember back in Algebra 2 and in pre-calculus, when we have something like this and we're trying to go to infinity, we look at the degree of the numerator over the degree of the denominator. And since they're the same, remember if they're the same, like negative 2x over x, you take the leading coefficients, right? So the limit here is negative 2. So remember this, like if the numerator is equal to the denominator degree, you take the leading coefficient over the leading coefficient. The numerator is less than the denominator, it's always 0. And if the numerator is greater than the denominator, there is no horizontal asymptote. Again, it's all coming back to you maybe, right? Okay, so we're going to kind of talk about why this works. Let's see how far I get in this. I have no idea how long this is. So it says, the third example will provide us a basis for developing our analytical process by which we can find limits at infinity for all types of rational functions. So looking at this, what do each of these functions have in common algebraically, and what do they have in common graphically? Well, algebraically, they both have an x on the bottom and a number at the top, right? Algebraically, they both are a constant on the top over a variable on the bottom. Do you agree with that? Some power of x on the bottom. What do they have in common graphically? Well, they both have the same vertical asymptote. Yes? Same vertical asymptote. And they actually both have the same horizontal asymptote as well. Ha, right? That's fun to say. So we talked about these rules in pre-calculus about the degree of the numerator over the degree of the denominator. It really all comes down to knowing that if I take the limit as x approaches anything, I guess 0 we can say, as x approaches 0, of any number over any power of x, okay? So I'm going to just say a constant over x to the n. Think about what we know about that. If I get closer and closer to 0 on the bottom, that's not what I want to say. I want to say infinity. As I get bigger and bigger numbers on the bottom, this gets closer and closer to 0, right? We never actually wrote this out like this in pre-calculus, but this is what we were doing. So we're going to kind of show that shortcut. Can you still do the shortcut? Yes. Is it nice to know why the shortcut works? Also yes, right? So there's a big paragraph here. I'm not going to bore you a bunch with this, but it talks about like knowing how we know to do the degree of the numerator over the degree of the denominator. Okay, so here's the big thing. If you divide every term in both the numerator and the denominator by the highest power of x, then you'll see that it works that you can take the limit, because we know 1 over x always has a value going to 0 as x gets bigger towards infinity, right? So on this one, infinity, I can't plug infinity in here, but if I divide by the highest power in the denominator, which is x squared, I would get x over x squared plus 2 over x squared over x squared over x squared plus 5x over x squared plus 6 over x squared. And I would get 1 over x plus 2 over x squared plus 1 plus 5 over x plus 6 over x squared. And again, as x gets bigger, these are all going to go to 0. So look what we're left with. 0 over 1, which is a 0 as an answer. Which is why when the degree of the numerator is less than the denominator, you're always going to have nothing left on top and a number left on bottom. But think about what happens if you do in this one. I'm going to show less work on this one. X squared is my highest exponent. So if I just divide everything by x squared, I'm going to get 2 plus 7 over x plus 6 over x squared over 1, because x squared over x squared, plus 5 over x plus 6 over x squared. And that, again, as limit goes to infinity, everything that's a constant over x is going to go to 0. And then look what we're left with. We're left with those leading coefficients. And the leading coefficient is 2 over 1 or 2. And you can see that that's your horizontal asymptote in that problem. So numerator less than the denominator. This is numerator equal to the denominator. And then look at the third option. Look at the graph. You can see it's a slant asymptote. And on this one, when you divide, the highest degree is x. So on the top, you'd still have an x left, plus 3 over x, plus, no, that wouldn't be plus 3 over x. That would be plus 3, right? Plus 2 over x over 1 minus 1 over x. So when the numerator is bigger than the denominator, look what happens when I take my limit. This goes to 0 and this goes to 0, but I'm left with x plus 3 over 1. And if I keep plugging bigger and bigger values in for x, this is just going to keep getting bigger, which is why the answer is infinity. So when you have something left in the numerator, you're going to have an answer of infinity or in negative infinity. Okay? Okay, I think I'm going to stop because we just have a lot left, right? I'm never going to get through all this. And so if you look on the next page, we'll start right here. These are kind of some special cases, and then we'll wrap it up in class, okay? I won't stop recording. Stop recording.